limits at infinity. I've been saying earlier we finished with infinite limits, meaning the final outcome of your function, right? Going infinitely up or infinitely low, right? But here we're talking about the limit at infinity. So here's a concept here. You got some function. Back in the days, and even the topic right before this, we're talking about limits going to a specific limit point on the x-axis, right? Okay, that's anything we've done prior to this point. But then that's not what we're looking at anymore. Here, limits at infinity, this is what we're doing. I'm letting x get close to either positive infinity. That's why it means limit at infinity. You see what I'm saying? You know? It makes a difference, right? We don't have a specific limit point on the x-axis anymore, but here's the graph. The graph may run whatever, right? But we want to look at, hey, what's the behavior of your function as we keep getting further and further out to the right-hand side. That's what this limit at positive infinity is all about. Am I making sense? Okay? But then in that way, limit at infinity, there should be another case, because why only going one way to the right-hand side, right? So the same function right here, you can also calculate limits as we let x get close to negative infinity. So this time it's really, we're heading back to the left-hand side. So we also want to consider, hey, how is the function behaving, right, as we go further out and further out to the left-hand side? See what I mean? Okay, so those two these are the definitions of limits at infinity right here. And that's what it is. Am I making sense? Okay, so basically that's what it is for limit at infinity. But then finding it takes a whole world of understanding. So we're going to, once again, take things in steps, right? Step by step, we're going to build it up. So, bring in another graph again. See, the graph may be doing whatever funny thing right here, but left-hand side goes one way, the right-hand side goes one way, right? See, going to positive infinity, we want to find out how the function behaving as we go further to the right hand. That's the reason why you may hear me and many other professors saying that limits, when x tends to, or when x is approaching positive infinity, another way of saying it, we want to learn about this is about the right hand, see, going to positive infinity, right? The right hand behavior. Well, I'm saying that the right hand behavior, the behavior as your graph keep navigating and keep advancing toward the right hand, that infinitely far to the right hand. So people will a lot of times consider that as the right hand behavior of your function. Right? I mean, when we're speaking graphically in terms of the graphical interpretation of your graph. And so in that way, right here, when you have a function, you take the limit, you let x get close, get further and further out to negative infinity. Okay? We refer to that as, a lot of times we may also refer to it as left-hand behavior. Does it sound okay with those terminologies right there? All right, so just enough with that beating around the bush. Let's look at some actual problem right here, and then you will understand. So how about, so right now it's not even a formal example. Let's just look at a famous function like x squared here, for example. It's a function, right? Everybody knows that function. Okay. So what does the graph of that function look like? Yeah? Okay, I agree. So the nice parabolic shape right here, right? And of course, forgive me if I'm off scale or anything like that. You know what I'm saying, no? Okay, so again, I want to find the limits of this function f of x with the graph right here, but I want to find the limits for this function as we get to, let x approach it positive infinity. Okay? We let x approaching positive infinity. Okay? So that's the formal notation, the formal symbol for that. But then, in what I explained earlier, you see, graphically speaking, we understand this limit notion, right? This limit concept here as the right-hand behavior. See, when x gets close to positive infinity, right? That means we are studying what's the behavior of the function as it keeps getting to its right-hand and right-hand. See what I'm saying? We call it the right-hand behavior. So back to the particular problem that we have here. So now, what's the right-hand behavior of this particular function that has the specific graph in front of you guys here? As we get further on the x-axis, as we tend further out to the positive infinity, right? What's the vertical behavior of that? You guys see it? Yeah? It's what? It's pointing up. See what I'm saying now? So the function is doing this, right? As we get further to the right-hand side, it keeps pointing up. Am I correct? Okay? So now your answer for this one here, your answer is positive infinity. Needless to argue. Sounds good with that, Okay, but keep in mind, I really want to reinforce that term. I keep emphasizing that term, limits. When x tending to positive infinity, or when x is approaching positive infinity, we call that, in a more daily term, like the right-hand behavior of your graph. Right? So in that case, look right into your graph right here, the same function. How about taking the limit as x gets close to negative infinity? Okay. What's the daily language for this? We call that, it's the what? The left-hand behavior, right? Because we want to know, hey, what's going to happen to the graph vertically as we keep tracing out to the left-hand side, right? In the everyday activity, I keep telling my students, when you're looking at a graph, you go from the left to the right, right? But when it actually comes to this kind of problem, anytime it comes to this kind of problem, and this is the only place, when it comes to this kind of problem, looking at the right-hand behavior or the left-hand behavior, sometimes we have to go backwards. See what I'm saying? No? Because to study about the left-hand behavior, you have to force yourself to trace kind of like from the right to the left and further left and further left. You got the idea? So there's this instance, this only situation that you do need to look at the graph from the right to the left sometimes, right? Just to study about your left-hand behavior. So now, what does that do right here on your graph? Vertically. Yes, it's still rising up, right? There you go. So the right-hand behavior was found here, but the left-hand behavior now is found to be for this function. Also a positive infinity. See what I'm saying now? Right? Very good. So this is one demonstration problem, right? Now, I reminded you guys earlier about this, but see, we talked about, I briefly reminded you guys about the families of functions, right? We got the polynomials, the rationals, and all of those, right? And then the algebraic functions, right? And then we went on to exponentials and things like that. So the x squared right here is a quadratic, but yes, it's a polynomial in the end. See what I'm saying now? Okay, it's a polynomial, right? Like it stays in that, power, and then with another term with another lower power, and with another term with another lower power. This thing here is one lone term right here, only one x squared term. See what I'm saying? Right. But the reason I mentioned about polynomials is because now to get far on your journey about limits at infinity, let's bring back some pre-calculus stuff here. Do you recall from pre-calculus that any polynomial, right, has a what's so-called, as far as the characteristics, it has a degree, right? The highest power that being along the terms, right? That's the degree. And there's always a leading coefficient. And the leading coefficient has to be a non-zero value, right? But a lot of times when you're studying about a polynomial, you're studying the degree and the leading coefficient, and it will tell you a lot about your polynomial right there. See what I'm saying? So now, I'm pretty sure you have seen this, but you're not going to be surprised how we use that for calculus right here. So for polynomial in general, we have this table back there. For degrees of your polynomials, right? It matters between the odd degree and even degree. So even degree or odd degree. And then it also matters when your lead coefficient, the an right here, lead coefficient, an, is a positive number or a negative number. Okay. Right? There are two separate cases here. We want to learn all of those. So let's see how many people remember this. But when your polynomial has even degrees, right? The two sides will point in the same direction. Left hand and right hand point in the same direction. Either both pointing up or both pointing down. Okay. The example is still right here in front of you guys. This function right here is a polynomial, right? What degree is this? It's even degree. See how the two ends are here? They're both pointing in the same direction. Remember that? Okay, so back then in your pre-calc 1, they didn't call that the limit concept. They didn't necessarily bring in the limit concept yet, but now with the limit concept, here we are. So now anytime that your polynomial is in even degrees, right? Then we didn't have that in demonstration, but either the both sides point up, right, or both sides point down. I'm talking about the two end behaviors like that. See what I'm saying? No? So what matters here is about the leading coefficient. So when the leading coefficient is positive and the power is even on your polynomial, then the right end will point up, the left end will also point up, just like the x squared demonstration we were doing earlier. Okay, remember that? And now, since we're talking only about right hand behavior, that's why I'm leaving dots in between here, meaning it can do whatever in between, right? A polynomial can do whatever fancy thing in between, but right hand has to for sure go up, and left hand also points up. Right? Remember that. Right? So remember that from pre-calc 1 now? And so similarly, so now still, if our polynomial has even degrees, right? And the lead coefficient is negative, let's say for example, you guys have a graphing calculator? You can quickly graph it and verify, like say a minus x to the fourth, plus 3x, something like that, plus 1. Okay, go ahead and graph that. Right, and actually sometimes graphing it, right? Graphing it. So I don't really care about the actual picture of the graph, right? But am I expecting something like this? Left hand points down and right hand also points down right here. For those who were graphing, right? You see? Even power, right? Even degree. Lead coefficient this time, right? It's a -1. See what I'm saying? No? So whatever fancy thing that happened in the middle part of the graph, I don't care, but the two left hand, the left hand behavior and the right hand behavior, the two hand behaviors right here, they're both pointing down. So you guys now all agree? Right? As I keep talking, I have more people finish with their graphs, right? And then you guys are hopefully more convinced with that. More you guys get convinced with that. You agree with that then? Right? And so now that comes for us as a regulation right here. See, anytime that we're looking at even degree polynomial with a negative lead coefficient, left hand points down, right hand also points out, right? And then whatever in the middle, that's not our concern. Yeah. That's why, generally speaking, anytime your polynomial has an even degree, both ends point in the same direction, either both pointing up or both pointing down. See what I'm saying there? Okay. So now let me remind you another one here. And you don't need to graph it this time. You should be familiar with this one. Think about the x cubed function. Fx equals x cubed. Is this a polynomial? Oh yeah, sure. Why not? Right. So my observation right now is telling me that it's no longer even degree, but it's odd degree this time. Right. That's the only term, degree 3. Okay. The lead coefficient is 1. Right. It's got an odd degree with positive lead coefficient. Remember the graph of this guy? Yep, that's nice waterfall, kind of like this, right? If we're thinking of that as a waterfall, it falls from the right to the left, right? You know what I'm saying, no? But here's the thing. That does reflect some generality about odd degree polynomial here. One end goes one way, the other end points the opposite way. See that now? One end goes one way, right? And then the other end points the opposite way. So the two end behaviors on an odd degree polynomial must point in the opposite direction. So here, specifically for this case here, our polynomial was odd degree, positive leading coefficient. Right end points up this time, right? And left end points down this time. You see what I'm pointing out right here? So that means we can put that here. Whatever happened in the middle, that's not important. Right end points up, left end points down when our polynomial is an odd degree with positive leading coefficient. And so now in the same way, with that understanding along that understanding right here, now think about it this way. What happened if it's odd degree And we didn't have a demonstration, but you guys are, at this point, are sharp enough to see that. What happens if we have an odd degree with negative leading coefficient? Right hand behavior is going to do what? Drop down, right? And then left hand is going to have just rising like that. Okay? But surprisingly, this is comprehensive enough that covers the hand behavior, right? The right hand or left hand behavior for all polynomials. See what I'm saying? Okay? So with that table now to construct it, let me bring in a formal example now. Then you guys will be amazed how much. See, but you should always value those days that you learned pre-calculus. They designed those classes for a good purpose. So let's call it example 1. Right. Find the limits. And by the way, see, this is a completely brand new topic, limits at infinity. That's why I'm restarting my example numbers. Okay. Positive infinity. Right. So before we tackle it down, what do you recognize about this function? It's a polynomial, right? The function we have here is a polynomial. So, and then the problem is asking us to study about the right hand behavior. See, x get close to positive infinity. You know what I'm saying now? So the way how we see that right hand behavior, we want to study about that, right? We want to investigate that. So for your polynomial here, so everything that matters now is that check out the degree, right? And check out the lead coefficient in terms of being negative or being positive. That's all, right? So what's the degree for your polynomial here? The degree here is 100, right? Even, right? Sounds good? Okay. An extra note here. Lead coefficient, or a lot of times people also notate that as AN right here, the coefficient that comes with the degree n right there. Lead coefficient is 4, right? Is that positive side or negative side? Positive. Sounds good? Yeah.
Why do they notate leading coefficient like that?
What's that?
Why do they notate leading coefficient?
Because right now in these days when I'm teaching, when anyone is teaching, it's rushing, so we tend to skip symbols and all that, but a polynomial is defined as a sub n times x to the some power n. Okay, and then plus some a sub n minus 1 with x to the n minus 1. The idea is we arrange that in powers, that whatever n is the highest power you recognize. You see what I mean? And so the coefficient that goes with that, right, we call it the an coefficient. And that's where we call it as the leading coefficient. Okay, and that's why. So when you back at your pre-calc 1, where they formally gave you a definition. And yes, they gave you that form, right? An times x to the n plus an minus 1 times x to the n minus 1. And then we keep reducing down to, the power 1, power 0, and all that constant term. Okay. But then here, I'm assuming a little bit that you guys have seen that before. So, and then it has become kind of like a routine that people call an being the leading coefficient. Okay. So leading coefficient here is positive, so that means what? It has to be according to that chart, right? The right hand behavior, the behavior here has to go infinitely up, right? So that means, right, 4x to the 100 minus 7x to the 10 plus 40, right? This limit here as x goes to infinity, right? It says positive infinity. That's how we're answering it. See how easy that is right there? Okay, but then the work will become more intense as we study further into this. But right now, that chart that you guys have learned covers all of the polynomials. We have an easy access to all polynomials. See that? Okay. So let's continue on that topic about limits at infinity. So we've got into so we understand that limit at infinity means that we're learning about the left hand behavior and the right hand behavior of a function specifically, right? So now let me bring in an actual problem here. Because yesterday, in the earlier lecture, we were only learning about how to find these limits at infinity for the polynomials. But now let's get into something more specific right here. Let's look at this function, 1 over x. Let's look at the limits for this function as x go to positive infinity. Okay. So this is just a problem I bring up to promote the idea right here. So unlike the x squared function that I have done earlier, I explained the x squared function in terms of a right hand and left hand behavior completely graphical, right? But here let's go back to table of values. So we departed away from table of values for a little while, and then let's come back, because you see when we're learning a completely brand new kind of limits problem, table of value is the only way for us to get through. So I'm going back to table of values. So now it's limit as x go to positive infinity. So that means similar idea. We pick a starting point. Well, the function here is 1 over x, so a starting point on the x-axis, you can go with a 1 over here, right? And 1 is completely okay to substitute into your function. See what I'm saying? No? And then, but here's the thing, to indicate going to positive infinity, we're gonna keep letting x get bigger and bigger and bigger in a positive way. So how about after that we jump to a 10 again? See what I'm saying? No? And then even after that, I jump to 100, okay? And then after that, I jump to about a 1,000, or even 10,000. See, that's how I'm indicating these are the sequence. This is a sequence of x values, right? Indicating we're getting larger and larger positively. So we're using table of values, but this time we're using a sequence of values that indicating the x value keep getting larger positively, getting larger positively. That's how we're indicating it. All right. Now you guys go ahead and have your calculator ready and help me out with the calculation here. That should be simple enough with this function, with a function like this. So our function is 1 over x, right? When x equals 1, the output is needless to say 1. Right? But what about when it's equals to 10 over here? 0.1, okay? So the value jumped from 1 to 0.1. I'm talking about the vertical value, right? And then what about when x equals 100? 0.01. Now, so far we've gotten to 3 values. What seems to happen to these outputs right here? They keep getting small and getting small, right? Okay? Keep going. What about when we have x equals 1,000? 0.001, right? Easy enough, and it's still getting smaller. But does any one of these values, I mean the outputs value, does any of these values hit 0 yet? No, right? Or not even negative, right? Okay, let's continue. How about 10,000? 3 zeros here and a 1. See what I'm saying? Now is that enough for you to start saying some kind of conclusion about where the function's output here is going as x is keep getting larger and larger? So what do you say here? As x approaches positive infinity, right? Our function becomes, the function output approaches, or it gets close to 0. It comes to that limit, 0. You guys following? Okay. So graphically speaking, the graph for 1 over x. Now I'm talking about x getting to positive infinity, so allow me to draw only 1/2 piece right there. But the 1 over x function has one famous piece. Observe my hand drawing motion right here. As x getting further and further to the right hand side, you see how it gets lower right there? And it gets lower and it keeps dropping down, but it will never actually hit the x-axis. Are you following with that explanation of mine? Yeah. Right, so that's one piece. So what about the same function, 1 over x? Right, same function, but let's consider the left-hand behavior. So let's let x, right, approaching negative infinity. Okay? We don't want to rush into the graph. Because I can't assume that everybody will remember the graph so clearly, right? So we stick with table of values. It's our closest reach again. So how do we indicate x value getting further and further negative? Getting more negative, more negative. Well, we pick a starting point, right? You guys want to come up with a starting point? -1, okay. And what's the next one to indicate being further negative? Go. 10, right? Negative 100, right? Just like that. Negative 1,000, negative 10,000, right? See what I mean? Okay. Now these values are about to be substituted into your function. So your function is 1 over x. We're substituting these values, so -1 substituted into your 1 over x function gives me a -1, right? -10 substituted into the function 1 over x right here will give me -0.1. You guys following? The calculation is simple enough, right? And then -100 substituted into the function is now going to give me -0.01, right? And so on. You can see that. See these values, they go from -1 but then less negative, right? It's still negative, but less negative. You see the magnitude of the negative being now only a 0.1, right? So negative and less negative and less negative. They're still negative, but just less negative. Okay? And so now we're talking about the next one here is negative 0.001, right? And then the next one here is negative 0.0001. You guys agree still? Okay. So what do you suggest? Yes, these values are all negative, but they're getting less negative and less negative and less negative, but they're still negative, right? So even if you go to negative 100,000 and substitute it into your function, you're still going to end up with negative 0.0000, right? 1. So now do you have a suggestion, a prediction about where the output value for this function go? As x gets further to negative infinity, it's still a 0, right? Still a 0. So this time allow me to draw the graph like this, and you will see the consistency. You see, we're starting out with somewhere on the x-axis, right? And then we get further to the left-hand side. You see how I'm drawing that, right? So the vertically, my graph is rising, making its way, try to hit that line. I'm saying just only try to hit that line, right? But we'll never hit, so it will permanently stay negative, stays below the x-axis, but keep getting closer and closer. Okay. All right, so that's the idea. So now all of a sudden you recognize these are some two special ones. And this is some among the special ones in terms of the limit at infinity right here. So it's a special limit, but it's not a. So among the limits at infinity, we got a couple of special ones, right? Something to nail down for sure. Our function 1 over x. As x is getting to positive or negative, so these are really two problems. See what I'm saying now? Right? For the 1 over x function, as x is getting to positive or negative infinity, both ends here will give the function approaching 0. Agree with that? Yeah? And then let's explore a little more. So I'm going to have to take this work out. All right, so let's keep a table, the empty table here ready for action. Now I'm going to come up with some new function. So what about 1 over x squared here? If we want to study, we want to investigate the right-hand behavior of this function here, right? What's going to happen to the function output as we let x get further to positive infinity? Okay, so go ahead and write it down. And we're going to use table values to estimate, to predict. So it's not really a left side table, left-hand side or right-hand side. Now we're talking about one way we're going to the right hand, right? And we consider the right-hand behavior of your function, where it's going. And then on the other hand, we're trying to look at getting further and further to the left hand of your function. Okay. All right. So our function now is 1 over x squared. Right? So the first value at start here is easy, right? X equals 1. When substituted that into your function, it's going to give me simply just 1. Sounds good. But when x equals 10, right? Now be careful. Your function here is 1 over x squared. So that means it's really 1 over 100 in the denominator, right? So that's going to make it 0.01. Right? Now 100 substituted into the function. Now go ahead and use your calculator and get me that value. Remember, it's 1 over x squared. Should be that value. 0.0001. Right? So these values are still positive, but they get smaller and smaller, right? And still seems to be above 0 as far as the observation is going. Right? Go ahead and substitute in 1,000 for that. And I don't think we have to go to that extreme being 10,000. You see immediately what's going on right there. So there's no need to go really that far. Okay? 1,000 substituted into your function. So 1 over 1,000 squared, right? Now in my calculator, it should come out 0.0000, right? 1. You guys agree with that? 5 zeros and then a 1, right? Now that should be enough. I don't think I need to waste your time calculating another one. Like say we don't need to let x equals 10,000. You kind of have an idea what's going on here already, right? What's your suggestion? What's your prediction about where this function output is going? As we let x keep getting larger and larger to the positive side. Okay. What do you say? Yes?
0.
0. Just like that. And then about the same function. 1 over x squared. Let's look at the right hand, the left hand behavior. We're letting x get close to negative infinity on the exact same function. That's why right when I was erasing the board earlier, I was still retaining those two tables because we're going to use them anyway. But be careful with negative sign this time, because when we're substituting it in the square, it's going to make it all positive, right? You guys all following? Okay, so take your time, fill out the table right there. I'm going to give you guys about 2 minutes filling out the table. I don't think you need to go up to as far as negative 10,000. That's a little too much for everyone. We can take that out. It looks like a lot of you guys put your pens down, so I'm assuming you guys done with the table. Right. So check with me. Okay? So this one here gives me a 1, just like that. Try and pause at 1 actually. Right. And here gives me a 0.01. This is a 0.000. And this is a 0.00001. Okay. You guys agree again? Okay. What do you say that prediction has to be? Right. It's going to be another 0, right? So how is this consistent? How is our work here consistent with the graph? Right? See, for this function 1 over x, where you've seen the graph before, if you're drawing it, here's how it looks. See, as we let x flow to the right-hand side, right? The vertical value keeps dropping and dropping, right? But we'll never cross through the x-axis. That's why it was that shape again. See what I'm saying now? Okay. Recall about that graph. And then left hand behavior. Now let's let x get close to negative infinity. You see how I'm drawing it right there? My pencil motion is keep extending further to the left hand side, right? And the vertical value keep dropping and dropping and become lower, get closer and closer to the x-axis. But we'll never hit. But both sides are all positive, stay above the x-axis. Okay. So that's the graph for our 1 over x squared function. So on this board, let's draw out another conclusion right here. We're sort of like tracing out some results right here, and we're going to make some even better generalized results. All right, so it looks like 1 over x squared, right? So as we're letting x getting close to either positive or negative infinity, the answer comes out the same, being 1 over 0. You guys follow with me on that, okay? And so now you can see that I purposely left you guys into that 1 over x. And then here, 1 over x squared, the point now is that think about, I don't want to, spend too much time just, tracing it down one by one right here. But the idea is these guys are all in one family. The function 1 over x to the end right here, x raised to a certain power. See what I'm saying now? Okay. And so now when we're working with that kind of function right here, then the limit here will be similar. Taking the limit to the right-hand side, right? It will give you a 0 on that kind of special function right there, right? So what's special about this function? 1 over x to a power. Sounds good? Okay. And then, so that's one important result that we can generalize. And then another one, same function, 1 over x to the n. Now we're taking x to negative infinity. The left hand behavior of that, it also goes to 0. So we also now have discovered two special little functions, right? Two special little limits. But these are the limits at infinity. Right? So they're special, but under that class of problems where we're working with the limit at infinity. And then for this function right here, the one hard truth about this family of function is that you see if the n here is odd, right? So now I'm talking about not only just 1 over x, not only just 1 over x squared. We're talking about 1 over x over x to the 99 power, for example. So if the power here is odd, then the graph will generally look like this. It looks very similar to the 1 over x graphic there. See what I'm saying now? Okay. And then when n is even. When n is even, the graph will look very similar, extremely similar to the 1 over x squared. Okay, but maybe it's more squeezed in. See what I'm saying now? Okay, and that's the idea of that. And that's how we came to these solid results. Sounds good with me on that? Okay. So now after unlocking the two secrets, I mean the two special limits right here. Let me rewrite it here so that I can have more space. So 1 over x to the n, right? Taking limits, x getting close to the right-hand side, right? Equal to 0, and then limits 1 over x to the n, right? X gets close to the left hand, for example. It's also kind of equal 0. So these are pages here with the graph. So now we're getting into limits at infinity. So I can now legally tell you, because we don't need to, bring in formal proof for every single topic we do right here. That's wait for some higher classes. Again, when you guys have a strong passion for math and eventually decide to go for a formal math major in calculus again, right? Then they're gonna really let you guys prove every single thing right here. But here I'm just simply gonna tell you this. You see all limit laws that we've learned, right? Remember those limit laws back then? Wasn't too long ago, right? All limit laws that we've learned apply. Okay? So take that understanding right there. It means, see, if you have some function, see, back to the polynomial that we've done in the earlier lecture, for example, like an x squared minus 4x plus 3, for example, it's a polynomial, right, with multiple terms. So when you're asked to find the limits as x go to infinity, yes, we already learned one quick solid tool to decide, right? But in the end, it's still true. It's still true that you can do one separate limits, right? For that, as x go to infinity, and then subtract one separate limits for x right here, right? Go to infinity and plus one limit for the constant term, thing like that. See what I mean? So all the limit laws are still apply. But for this for a function like this, we already had a one quick tool to give the answer, so we don't need to use the limit laws back then. But then the limit laws will still be useful in some other functions. Yeah. When we step outside of the polynomials that we've learned. See what I mean? Okay. And so now that's just a quick demonstration to allow me to start bringing in some examples. Example 2, we want to evaluate, right? Evaluate. We want to take the limits as x goes to. You guys want to pick a choice for me between positive, negative, infinity. Which one would you like to pick? Okay. Positive, infinity. Okay. Now, let's call that part A of the example. Okay. So now once you've written it down, think about it. And this is sort of like scratch work level before we put that into the formal steps, formal reasoning here. But see, according to what I said earlier, all limit laws apply, right? All limit laws apply means in a way how our function looks. We got a quotient right here. See what I'm saying? No? So limit law says that you can do one separate limit on the 11x plus 3, right? And then we divided that by whatever that will come out for the limits, x to infinity, on the bottom function being the 5x squared minus 10x plus 11. You guys following? Okay, but this is how things starting to get a little dangerous right here. So yes, limit laws apply, but a lot of times, think about the earlier in the earlier lecture where we were doing limit laws. Limit laws don't always work well. A lot of times, right? And so think about the situation right here. We directly use the limit law here. Now, if you're looking at limit of as x goes to positive infinity, just focusing on that function 11x plus 3, for example, what kind of function is this? Yes? It's a linear, yes. But more generally, we put a linear function into that polynomial class, right? So, degree 1, odd degree, positive leading coefficient. So what do you know about the right-hand behavior here? For this function, just on that function 11x plus 3, it's going to go to infinity, am I correct? According to what we've learned previously, right? So same way right here. What do we recognize about this function? Anyone? Yes, it's a polynomial again, right? See, because the function here we have is a rational, so it's a polynomial on top. Specifically, it was a linear. Here is a polynomial again, right? Specifically, it's a quadratic. You know what I'm saying now? But quadratic is not important. What degree is this? Even degree, right? And then leading coefficient, positive, right? So that means the right-hand behavior is going to have to also point up for that. See what I'm saying now? So the denominator will give me a limit like this, technically, right? I mean, just the denominator or the numerator individually will give me those two. But now that means, in theory, we put these two as a fraction, right, as a ratio. But then that's where the danger comes in right here. This is where the danger comes in. I keep having students canceling out this, it gives me a 1, which is not true. See what I'm saying now? Now, I don't want to get you guys into too far of that, but these are, you have to understand the infinity and the infinity, these are growing quantity. They keep getting larger and larger. So there could be the fact that some guy is getting faster, getting bigger faster than the other guy. Are you understanding what I'm saying now? This infinity may grow large, faster than the other infinity. That's one case again. Or this infinity in the denominator may grow large, faster than the other one. And so in that case, just simply an infinity over infinity, never cancel and make it a 1. Okay, never do that, because those are not exactly a number. Are we clear with that again? This is why the precise term for this, anytime you have infinity over infinity, precise term for this is we refer to that as an indeterminate. Okay, it's an indeterminate. That means just simply in this setting right here is not enough information for us to determine the final answer. You guys good with me on that? Okay, so that means apparently, like I said, limit laws apply, yes? We are allowed to use the limit laws, but in this case right here, limit laws simply just didn't work. Okay? Didn't work means that it didn't get us anywhere. And so now, before we use the limit laws, now I'm going to take away this route right here. Using limit laws directly ran right into an indeterminate. And so here's how I'm doing. So I'm going to use some algebra before proceeding with the limit laws, right? Before even taking the action of doing limits, I'm going to do this. I'm going to multiply the denominator by the expression 1 over x squared. See what I'm saying now? And then with the rule of algebra, if you decide, so doing this here down here is a decision, a choice right there. And I'm going to explain the reason why I made that choice later. But now, right now, multiplying 1 over x squared to the denominator here is a choice. But if you decide to do so, make sure to multiply algebraically. Try and multiply this same expression to the top as well. See what I'm saying? No? That's the way how we do in algebra. So I'm going to multiply the exact same 1 over x squared to the numerator. Okay? I wrote that in the red color right here, red ink right here, so that you can see there's something special about that. But right now I'm pointing it out. It's just simply a decision, a choice I've made. But now let's look at the usefulness. So we're now playing around with the algebra. So you gotta get your algebra going, otherwise it's hard to move on with these kind of stuff here. I'm not doing any limit yet, so I'll leave the limit here hanging around. Sounds good? Okay. But now think about the consequence of multiplying the 1 over x squared to each of these numerator and denominator. 1 over x squared multiplied with 11x, it cancels out, give me 11 over x, right? You guys agree? Right? Well, that's, and first thing from algebra, that expression will get distributed to each term, right? And then things canceling out to common factors and all that, and you guys are way beyond way beyond algebra, so allow me to, skip some of the minor explanations, right? Because I'm assuming you guys know that. So multiplying that x squared to 3 right here gives me plus 3 over x squared, because there's no cancellation. Agree with me on that? Right? And I'm doing the same thing to the denominator. 1 over x squared multiplied with that first term right here. Okay? And some cancellation is going to happen, right? So the x squared cancel with the x squared, it gives me a 5. Sounds good? Okay? And then 1 over x squared distributed into that middle term, some cancellation happens, it gives me a minus. It gives me a minus 10 over x. Agree with the algebra again? Okay? And the last one here is plus 11 over x squared. There was no cancellation done for that specific term. Sounds good? All right, so now here's the shock. So after doing that, right, we let our expression into something that looks way complicated. But here's the thing: this is where limit laws successfully apply. We can properly apply limit laws. So yes, we can do one separate limit. That's x to infinity on the numerator, which is two terms: 11 over x plus 3 over x squared. You guys follow it? Okay. And then limit law says you can also find one separate limit. for the denominator, right? With the three terms, 5 minus 10 over x plus 11 over x squared. You guys see what I'm doing there? Okay. And then, so anyone need time to get caught up? And so in the next step right here, the next limit laws I'm applying, see I can do the limits, that same limits, right? I can do that term by term in the numerator. So that means I'm going to have one separate limit as x goes to infinity for the 11 over x. You guys following? Right? Plus one separate limit, same limits to infinity for the 3 over x squared. You guys with me there? Okay. And then I'm doing the same for the denominator. I have 3 terms this time, so the same limit problem can get done by 3 separate little ones, right? So limits x to infinity on the 5 right there, right? Limits. Subtract the limits for 10 over x, right? As x getting close to positive infinity. And plus, right? Limits of 11 over x squared as x getting close to infinity. Then one more optional step, and you guys will see everything clearly. One more optional step. I mean the constant 5 right here, let's hold on to that constant 5. Right? So limit of the constant 5x going to infinity of 5, let's hold on to that, right? And then the first term in the numerator, is 11 over x. 11 over x really means 11 times 1 over x, right? You guys with me there? So I see 11 here as a coefficient to multiply with the 1 over x. So my point now is that term I can rewrite it as basic limit laws again, right? I can keep the coefficient out and simply just take care of the limit of 1 over x when x gets close to infinity. You guys follow it? Okay? And then the similar thing, I can argue for this. Plus, now I see 3 as a 3 times 1 over x squared, right? So the 3 is a coefficient. I'll keep the coefficient here and then multiply with the limits of 1 over x squared. See what I mean? Okay? Right? And then the constant term here, I told you the roof earlier, let's hold it here for now. I'm subtracting, and then the same way with that, right? A 10 over x, I see that as a coefficient. 10 is multiplied with 1 over x, right? So I'm subtracting the 10 coefficient, but then that coefficient will eventually multiply with the limit of 1 over x. As x gets to infinity. You guys with me there? Right? And the last term here, I'm going to write it as 11 multiplied with the individual limit for 1 over x squared. We good with that then? Okay. Did you guys see the victory around the corner already? Okay. So, because now I've turned the problem into a whole bunch of limits of the 1 over x and the 1 over x squared, or 1 over the power of x, right? So what have we learned just earlier about these results right here? See? No matter what power that is, right? But this 1 over x to a power, you go to the positive infinity or you go to negative infinity, it's all going to come out to 0, right? And so now that result right here is going to be brought into our problem. So now, so here it goes. 11 times 0, right? So that gives me a 0 on the first term. 3 times 0, right? So that gives me a 0 on the next term again, right? And then now limit laws apply again. So when you take the limit on a constant term, right? No matter, see your constant function goes flat like this, right? So no matter how far you go to the right hand side, it's still going to remain just that same constant. See what I'm saying? No? So needless to say, that terms here gives me the limit being 5, right? So it's the same exact limit laws again, still holding. Okay? And then what's that giving me? It's another 0, right? So I'm subtracting a 0, I'm adding another 0 over here. See what I'm saying now? Now feel free to do the final calculation. Now you got all the variable values again. Okay? So what does that give now? Okay? That's all just 0 over 5, which is a 0, right? See how it's done like that? Right? So that's how we did the work. That's how we did the work. And so now let me tell you, let's roll back to that point of, so that I can explain a little more. So the procedure here, the work I did was that I multiplied the 1 over x squared as a choice, right? I multiplied the 1 over x squared as a choice to the top and to the bottom, right? And this technique right here applies, work well when we're looking at a rational, taking limits as x to infinity of a rational function. Okay? See, polynomial or polynomial. Right? So in our old term, those terminologies from pre-calculus, we call that as a rational function. So, but then what made me decide to go with 1 over x squared? Simply because x squared is the highest power in my denominator. See what I'm saying, no? I recognize that my denominator here, the highest power in my denominator is the x squared. You guys following with that? Okay, so you look right at that 5x squared term right there, right? That term right there got the power 2, right? And that's the power, that's the highest power. Am I being clear? Right? So in that way, that's what made me decide to do so. So for this problem right here, I multiply 1 over x squared because the highest denominator, I mean the highest power in the denominator is the 2. Sounds good? But then before I move on to another one, let me make one more conclusion. I mean one more remark here for you guys. I mean one more thing that trigger your attention right here. The rational expression we have currently here is having a lower degree on top. You still remember what the degree is? Yeah, we just talked about degrees in the earlier lecture, right? So this guy here is what, degree 1, that guy is degree 2. See what I'm saying? So that's not important, but the idea is lower degree on top, higher degree at the denominator. See that? Okay? And so I did the work, and then I chose the x squared because I chose to multiply with 1 over x squared, but the x squared here specifically came out from the degree, from the denominator. Sounds good for me on that? But then it looks like right now I only explained that because the problem here is a lower degree on top and higher degree at the bottom. Let's see if it works out the same way in some other cases. So let me bring in another one, shall we? Okay. Okay. But then here we want to go. Here you guys can pick. How about we did going to positive infinity earlier, right? Let's do that to negative infinity. The point now is that the technique I'm about to show you in this class of functions right here is pretty independent with the left hand and right hand. You do the same technique, right? Even though it's we switch to going to negative infinity, we still apply the same technique with that. Okay, so you now with some quick insight, you can see that hey, if you apply the limit laws immediately, limit for the 3x to the 4th minus 4 right here as x getting to negative infinity, right? And over limits to x to negative infinity of that 5x to the 4th plus 10x. Will this give you an answer? I mean, individually, what does that one give? Left hand behavior goes to the left hand. So what will be the left hand behavior of this polynomial? Infinity, right? On infinity as well, right? Even degree, right? Positive lead coefficient. Sounds good? Right. What about the one in the bottom right here? Left hand behavior, right? Due to that the negative infinity x is getting close to negative infinity. What do you guys see about this? Even degree, also a positive leading coefficient, so it goes to infinity again. But this is where it's indeterminate. You won't find a definite answer out of that, right? And so that doesn't count yet, right? It's an indeterminate form. So it's indeterminate. So we're going to do that similar trick again. Rational expression. So this time I am going to multiply the top here by 1 over x to the 4th and multiply the bottom here by 1 over x to the 4th. Okay, read that? And then you're starting to click even better with how I made that decision of multiplying the 1 over x to the 4th, right? So it looks like still I stay with that same criteria that I tackle down right in the highest power in the denominator, trying to get the 4th power. Okay, and then so that's what made me to decide using the 1 over x to the 4th power. Okay. All right. So now you guys have seen the action from one problem earlier, so we can start moving a little faster now. So the problem, even though it's changed to a left-hand behavior, x to negative infinity, but it shouldn't violate any of the way how we work. So distributing the 1 over x to the 4th, right, to each of the term in the numerator here. First term comes out being 3. You guys agree? Right? So next term comes out being minus 4 over x to the 4th, right? And then distributing that 1 over x to the 4th to the two terms in my denominator here. First term comes out being a 5, right? And the next term comes out being a 10 over what?
X to the third.
X to the third power. Right? Right? And so that means using the basic limit laws, now basic limit laws will apply. We can do one separate limit for the 3 minus 4 over x to the fourth, right? And we're dividing that by limits, right? For 5 plus 10 over x cubed, right? These two limits both approaching negative infinity. And then yes, we can further rewrite this as one separate limit for the constant term 3 in the numerator to infinity. Infinity actually. And then subtract limits for 4 over x to the fourth, right? X to the negative infinity. In the same way here, we have one separate limit for the constant term 5 in the denominator, right? X to negative infinity plus, right? And then there's a limit for x to negative infinity on that 10 over x third. Now the next one I'm about to write may be skipped. The one that I was doing earlier, that we isolate this out as a coefficient multiplied with that, right? That can be skipped a little bit. So what I'm talking about is this step right here. Okay, to the infinity minus a 4 times limit of 1 over x to the fourth, right? Writing things like this. Yes, you may skip this little step again, right? And then 5, right? Negative infinity plus, and then there's a 10 times, right? Limits x goes to negative infinity, right? Or 1 over x cubed. Right now I'm demonstrating the idea, so I have to tear it down to the level so that I can convince you. But later on, when you write your actual work, you can, right from here, you can start picking in the answer. So, limit for a constant goes to the same constant, right? That term right here, we've had that result we proven earlier in the form of 1 over a power of x, right? And so, regardless of going to the right end or the left end, it's all gonna come out being 0. You guys with me on that still? Right. And then that term here stays a constant, right? Plus 10 times, right? And then that here, once again, must be a 0 for that limit. And so now in the end, right? Our final answer comes out being 0, 3 minus 0, 5 plus 0, right? 3 fifths. You know what I'm saying? That? Okay. So we found an answer. So this limit here comes out with the answer being 3 fifths. So later on, when you do your actual problem here, as long as you get to that point where you individually tear it down to the limits of each term again, right? And that's how you can make that directly into this. And that gives me a 0 here, and that limit here gives me a 0. You don't need to go all the way through that. I mean, that I can let go a little bit, right? But for this class right here, the algebra and what made you decide to do the algebra things like this before you get to the answer again, that's strictly required that you got to show those convincing reasoning for that. And then when we finish with this kind of problem, I'll mention some more the reason why, I got to restrict that a little bit. Any calculus instructor who is responsible for the students' learning, there should be mentioning that. Part C here. One point about. Alright, so for this limit, once again, you can quickly, and think about it on scratch work here, you can quickly see that if you apply directly the basic limit laws, right? As I said, the basic limit laws apply in a lot of these, but sometimes you got to be careful. So if you apply immediately basic limit laws into this, so 3x to the fourth plus x plus 5, right? And then as x go to positive infinity, right hand behavior, right? And the top here specifically is a polynomial, right? And then we're dividing that by whatever limit that comes out from the denominator here, x squared plus 3. So both top and bottom, they're all polynomials. So the one on top here is an even degree polynomial with lead coefficient positive, right? So the limits, the right hand will come out being positive infinity. You guys agree? The one in the bottom here, when you take the limit here, this polynomial has another even degree, right? And the lead coefficient being a positive as well. And so right hand behavior comes out another positive, but this is where it's indeterminate, right? So don't rush into that route. I'm not saying that we can't go with basic, we can't use the basic limit law, but immediately right now it's giving an indeterminate. Indeterminate, right? And we will learn more specifically about how we can handle these indeterminates in some other problems that later throughout the quarter. So now, at this point, being indeterminate means we have to roll back and think about before we apply the basic limit laws immediately. There's something else we can do, right? And so now, another observation. Once again, what I have here is a rational function, right? Just a little bit of observation, but the degree on top is this time higher than the degree of the denominator. You guys follow with that, okay? But then that's not a big deal, it's just something to notice, okay? But still, it looks like the technique we've been using in the first two problems in this example is we multiply with the 1 over the highest degree in the denominator, right? See what I mean? Okay, so let's see if we use that again here. Let's see if we use that again and any success can come out for us. So from the denominator, I recognize the highest degree here is the power 2, right? So I'm going to multiply with the 1 over x squared, you guys following? And I'm going to do the same. I multiply that 1 over x squared to the numerator. Right? So, and that means now I'm just focusing on the algebra work. Nothing limits yet, right? Nothing as a limit work yet. So in the next step right here, I'm still going to keep the limits operation here, hanging there. 1 over x squared distributed for each term in my numerator, it gives me 3x squared on top, right? Plus, and then we got a 1 over x right there, if you guys agree, plus a 5 over x squared right there, okay? And then this 1 over x squared distributed here, we're looking at a 1 plus a 3 over x squared. Sounds good? Okay. Yes, we can now apply the basic limit law. It says we can have the limits, right? Or the 3x squared plus a 1 over x, right? Plus the 5 over x squared, right there. And then divided by the limits of 1 plus 3 over x squared. Yeah. Okay. When x gets close to infinity, when x goes to infinity. And then again, further basic limit laws allow me to find the individual limits of each of these terms, right? So here I'm looking at limits for the 3x squared term, okay, as x gets close to infinity, plus, now the next one here is the limits for the 1 over x, right? As x goes to infinity, plus the limit for the 5 over x squared term. Okay. You guys are still with me? Okay. And then we divide that by the limits for the first term is just a 1, right? As x gets close to infinity, plus, we have the limits of 3 over x squared, right? Over x to infinity. See what I mean? Okay. We have worked often enough with these problems to the point that now I can also sort of like push it to the next level a little bit. We have been agreeing, we have already discovered that, hey, when it's 1 over a power of x, right? And then we take the limits as x get to infinity or 1 over a power of x, where x gets to negative infinity. Any one of these will turn to a 0, right? And we have proven that successfully, right? So we can kind of extend. So these two right here, okay, we have some extension. The extended version here is that now you can also allow legally. So that from this point on, you can rush into your step here. If simply you have a coefficient, not necessarily 1. You know what I'm saying? Now, a coefficient over an x to the n, like that, a power of x. Okay, x to infinity, that comes out as 0 as well. Right? Or simply a coefficient over x to the n, but then you're taking the limit as x to negative infinity. That will also come out as 0. So we extend these fundamental understandings right into a better version, so that we can make the steps shorter a little bit in terms of our work. Am I making sense? The usefulness of what I just now brought in. Is that now we're ready? I'm not sure about that one, so let's hold it there. Right? This term. So whatever there, we'll consider that later. This term goes to 0, right? That term coefficient over a power of x, right? Take the limits to the right hand side, you go to 0 again, you guys agree? It's a constant function, right? So taking whatever limit it is, the function stays flat, stays constant, and then that term right here is a coefficient over a power of x. So taking the limits to the right hand side, you go to 0 again. You guys agree on that, okay? Okay, so these are all 0 and then divided by 1 in the denominator. What about that one, that long term again, the 3x squared, as we let x to infinity? What's your argument on that? It goes to infinity, right? But what's your reasoning for that? Yes, it's a positive leading coefficient, right? It's a polynomial, only one term, but it's a polynomial, right? What degree is this? Even degree, right? With positive coefficient. That's why we know for sure that this thing has to go to positive infinity. So now do you have a solid answer here? One term keep growing large, right? All the other terms grow to either 0 or go to a 1. So yes, you are convinced now that your final answer is infinity. See what I'm saying? Okay? Your final answer is infinity. There you go. So after 3 problems, specifically in example 2 right here, I was all focusing around the rational expression, right? How to find a right-hand behavior and left-hand behavior, and these are, I managed to do these things on, random choice and that, right? And it works the same way. The technique here is that we multiply with the 1 over the highest degree in the denominator, from the denominator. See what I'm saying now? And then we learn, sometimes when it's, when the degree on top is lower than the degree at the bottom, right? And we already learned some results like that. And sometimes the degree on top and the degree at the bottom are equal, right? And the case right now, the degree on top is higher. And then, but in any case here, for you guys here, the formal work is that we always going to multiply algebraically 1 over the power of x from the denominator, the highest power of x in the denominator. See what I'm saying now? And the work came out of that. But now, just for you to know, don't use this as your reasoning, but it's sort of like a shortcut to check your answer, to double check your answer right there. But I'm showing you because I feel guilty if I didn't, right? But make sure do not use this as your formal defending reasoning. Because as a formal calculus student, you guys don't answer the things like this. See, the idea now is that you're looking at a p of x, a polynomial over another polynomial, right? See what I mean? And then the problem we're working with here is x going to either positive or negative infinity. You guys see what it was? That's the generality throughout example 2 right there. So there was a first case we did when the degree, right? When the degree on top, the degree of the polynomial on top, p of x, was lower than the degree of the q of x in the denominator. That was what we did in part A right there. See what I'm saying? The result, no matter going to left hand or right hand, the result will always come out 0, right? This limits to positive or negative infinity of the p over q will always go to a 0, a hard 0. See what I mean? But remember, that's only a way for you to double check your answer, because a lot of times you come to an answer but you feel unsure, you don't want to repeat over the steps and repeat over and over. So there's a way for you to double check like that. So only use that quick trick like that, right, as a way to double check your answer, to double confirm, but don't use this as, in your written work, that, hey, this polynomial, top is lower degree, so it comes to a 0. I don't want that kind of answer, that kind of reasoning in this class. Are we clear with that? Okay? You guys are a formal track calculus student, so you are required to learn all of those the solid methods, okay, rather than just shortcuts. Okay? The case that happened in problem part B of the example, the degree on top was equal to the degree at the denominator. You guys follow with me with that? So when it comes to that case, this limits will come out to a finite number, a finite value. But this finite value right here is the lead coefficient of p of x over the lead coefficient of q of x. Okay. For short, people say it's the ratio of the two leading coefficients. Okay. See what I mean? Okay. take whatever the leading coefficient in your numerator and divide that by the leading coefficient of your denominator. That gives you the final answer for this. But once again, this such a shortcut that is only valid, right, for checking, and I don't want you guys to overuse that and then use that as your reasoning in your written work. Right? So, and then the third case again, there's no clear-cut answer. There's no clear shortcut. So we just have to stick with the actual algebra. But sort of like generally, anytime that we have the degree on top greater than the degree in the denominator, right? Then this limit right here, right? The limits of the key of x, q of x may equals a positive infinity or may equals a negative infinity. I'm talking about in any of the cases right here. It may come out positive infinity or it may come out negative infinity. It all depends on the way how we check. Remember that critically speaking, when you go through that process, really, at some point you will run into a remaining polynomial, right? That's where you check to see right-hand behavior or left-hand behavior pointing up or pointing down. See what I'm saying, no? Okay. So that's some of the results that you can quickly check with them. But once again, never use that as a formal reason for that. It's because it's never been formal. Okay. That's all that part A. I do intend to give another one after this. So in the way I was saying that we can apply basic limit laws, right? A lot of times you will run into the setup where at some near final step, and then one function grows to infinity, and then another function also grows to infinity, and then the two functions in the beginning were added together. And yes, when you come to something like this, right, you can come to the immediate conclusion that the final answer, the final overall limits will also grow to infinity. So this is legally accepted, legally allowed. But then be careful. When it's infinity on some term, right, and then another term grows to infinity as well, but we subtract them, this is where you don't rush into a final answer. The worst thing, equals 0. No, it doesn't. See what I'm saying now? See, because people think it's infinity minus infinity equals 0, but no. Remember, there could still be some terms growing faster than the other terms, so in the end it turns out that it leaves a difference of being bigger and bigger and bigger. See what I'm saying now? So infinity minus infinity, there can be so many different answers. It's formally, it's an indeterminate form right there. Okay? So don't rush into that, right? This form right here, this is legally accepted. But this form right here is another indeterminate that we have to handle a little more carefully. So, why do I mention this? Back in this problem right here, you can think about it that way. See, basic limit laws tells you that, quickly as a scratch word, right? You can do one limit of the square root function, x squared minus 7x plus 1, right? And then x to infinity, and the minus, right? The limit of x to infinity. So now, that same way right here, limit law says you can take the limits inside of the root, right? X squared minus 7x plus 1. See what I'm saying? That, and that x grows to infinity. And then, so what's the limit for that? Yes? It's infinity, right? But it's minus infinity. What's the limits for the thing inside the square root? It's also infinity, right? So it gives me a square root of infinity minus infinity. But see, square root itself is a rising function, right? So as the quantity inside grows bigger, the whole square root is also still going to grow bigger, right? So my point is that we're still going to run into this infinity minus infinity. This is where it's an indeterminate. Don't say that the answer is 0. It's a no-no. Sounds good with me on that, okay? So much work to experience out, but it didn't work. So I'm going to have to take it away. So we can't go that route, right? So we try a different way here. Now here's how I'm seeing it. You see, remember I introduced about the conjugate pair before? It's a minus between these two terms. So I take the whole square root term as one thing right here. So I'm leaving the limits here on its own right there, right? The function was square root of x squared minus 7x plus 1. That's one term right there. I subtracted x, but now I'm going to purposely multiply. So I'm going to purposely multiply the conjugate. So the conjugate looks like the square root of x squared minus 7x plus 1, the whole square root term. But then the other term is a plus x. You guys read that? Okay. And then the beginning function here, we didn't see a denominator being displayed, right? It means it was an over 1. Okay, it means it was an over 1. So that means I'm going to multiply the exact conjugate here to the denominator as well. So the rule of algebra says anytime you multiply an expression to whichever side in your fraction, right? Make sure you do that the same for the other side. So I did that multiplication to the top. I have to ensure I'm doing the same to the denominator as well. Okay, so x squared minus 7x plus 1, I use the square root plus x being multiplied in. So now my next step here, yes, still a limit problem. Right? But now I have produced for myself a fraction. The denominator here becomes the square root of x squared minus 7x plus 1, right? Plus x. The top here is going to give me, see, square root of x squared minus 7x plus 1 all squared, right? And minus x squared. You good with that still? Still on my way reducing the expression algebraically, so the limits is held on. Okay. The square cancel with the square root, right? It leaves me x squared minus 7x plus 1, no more square root, and minus x squared. Good? Right. So eventually the two opposite terms will get canceled away, right? We have in the denominator x squared minus 7x plus 1 inside the square root plus x. So everybody all agree with me on that still? So the x squared term are opposite, so we can cancel it nicely. The limit of as x gets to infinity, becomes minus 7x plus 1. And in the denominator, we have x squared minus 7x plus 1 plus x outside. So we have come to a point that's a little challenging right here because it's got involved square root. It's still got a fraction. It's still got a fraction in here. See what I mean? Okay? But then in the denominator, it's got some square root involved. Now let me tell you what. The good news is I call something like this. In my term right here, in my own terminology, I call something like this a rational like. Right? This is what I call rational like right here, because it's the way we handle that. It's not exactly a rational function due to the square root right there, but it will behave. It will work similarly to a rational. So what does that mean by it behaves or it works similar to a rational? So the top right here, what degree is that? Degree 1, okay? Make notice of that. But the way we have been doing so far, we've been looking at the degree in the denominator, right? But the degree in the denominator, here's the thing, outside of that, we got a power 1, right? Inside the root, we have a power 2, but think about it, the power 2 here, compensated with the root right here, is going to become just power 1, right? Because the power, like the root is a power 1/2, right? And then mixed to get canceled together with a power 2 inside right there, it's really just the overall power in the denominator, the highest power is a power 1. So you guys follow my argument on that, okay? So in that way, this is what I'm doing. I'm going to decide to, so I call it rational like. That means the way how I work with the problem is like how I've done that in the earlier example. I am going to multiply top and bottom by 1 over x. You guys see that there? Because like I said, my argument was that even though I spotted a square in the denominator, but it was inside the root, so it will cancel out and make it the highest power is just simply 1, right? So 1 over x. Okay. So I multiply the 1 over x to the top as well. Are we good with that? Okay. And so now, so in my next step, here's how I'm working it out algebraically. Limit problem, x to infinity, right? And then now you got, distributing the 1 over x to the first term, I'm looking at -7, right, plus a 1 over x, right? And then the next one right here, I'm looking at distributing. Let me just slow it down the step a little bit in case you don't remember too well with your algebra. X squared minus 7x plus 1 supposedly multiplied with a 1 over x, right? And then plus with the x here multiplied with the 1 over x give me a 1. You guys follow with that? But what do we do with this 1 over x multiplied with the square root? the plan here is that we can also bring that inside the square root, but here's the one thing. If you bring that inside the square root, make sure you square that, okay? When you bring an expression to the inside of the square root, say like an x right here, but if you're putting that inside the square root, you gotta put it as a square root of x squared like that, right? That's the most common thing right there. See what I'm saying that? When you bring that inside the square root. So, and what I said here was not entirely accurate yet, but at least that's the main theme right there. So here I'm doing limit to infinity, right? The minus 7 on top is there, 1 plus 1 over x is there, right? So now I'm going to bring this, I'm going to distribute that to those terms inside, but remember again, when you bring that inside the root, you got to make it square. So that means what? The square root here, well, let's keep it like this, x squared minus 7x plus 1. We multiply that with the 1 over x squared. That's what I meant, right? That's what I meant by bringing that to inside the root. Okay. And then eventually you can distribute that 1 over x squared to each term inside the root. Right? And then you still have a plus 1 outside the root. Okay. So now in my next step, I'm still keeping a little bit notation. Hold on here. Got the minus 7 plus 1 over x. Here, there's the square root expression. After distributing the 1 over x squared, I'm going to look at 1 minus 7 over x plus 1 over x squared, right? Plus 1. So now we are ready for distributing the limits here. Basic limit law says you are allowed to do one separate limit on top, right? For the negative 7 plus 1 over x. Okay? And then you can do a one separate limit for the denominator on the square root of 1 minus 7 over x plus 1 over x squared plus 1. And that further means you can distribute it. You can distribute the top here to the limit of the negative 7. Right? So x to infinity plus the limit of 1 over x, right? When x to infinity. In the inside right here, you can do limits separately for the square root term, right? 1 minus 7 over x plus 1 over x squared plus separate limits for 1 x to infinity. So I can see immediately that in my numerator it's going to remain just negative 7, right? No matter what limit it is. That term here goes to 0. Yeah. The limits outside of the square root can be now brought inside. So in other words, I will have square root of limits the negative 1, right? I mean 1 minus 7 over x, right? Plus 1 over x squared. Right? For x going to infinity, and then add 1 right here for that limit that comes to here. So you see how I'm slowly going through the steps again? Right? And now we're going to distribute the limits again inside of that square root in the denominator. So 7 plus 0 is, minus 7 plus 0 is a minus 7 in the numerator. Here I have square root, right, of a limit for 1 minus the limits for 7 over x, right? And then plus the limit for 1 over x squared, that be my square root. And then outside of that, we plus 1. These are all the limits going to infinity, limits going to infinity, going to infinity. We adjust that, minus 7. And so now things keep becoming easier. So negative 7 on top. The square root here says that limit gives me 1, right? That limit here is 0, that is 0, so it's a square root of 1 plus another 1 outside. So now in the end, I'm looking at negative 7 half there. Okay. And that is going to be my final answer. And then I just now changed my mind. And how about for this example, let's keep that at just one problem. That I want to introduce how you can handle this specific case where it's, the limits, infinity minus infinity limits, right? That indeterminate form. And then you can also get some experience with handling the root. But now let me call it example 4, similar problems. Everything we've been doing so far mostly focus on going to positive infinity, right? the limit, what we're doing here is to negative infinity. It's on the same function here, but it deserves your attention, so I put that as a separate example. So now allow me to mention some extra information here as well. So again, back to when it was a rational. All of those problems that we did throughout example 2 that we've done earlier, right? When your function is rational, then taking the limits, right, to infinity, positive infinity, or negative infinity, doesn't matter right hand or left hand. The way how we do that is just one solid way right there. See what I'm saying? We don't need to bring in any special treatments or anything like that. Okay? And we'll come to whatever limits here, but any one of this, the way how we're doing that is just one method that worked. And that method was to multiply, the 1 over the highest power of x in the denominator, right? But that was the method that only worked for the rational function right there. So independently with either you go into the right, the positive infinity or negative infinity, right hand behavior or left hand behavior. But now when you work with this function, right here, I purposely put in the going to negative infinity with a red ink right here to make it a little more the attention catching, right? Your function first off is no longer a rational. Yes, at some point I made it like a rational right? But in the end, originally itself, the function itself is not a rational function. So you need to take some caution. So when it comes to this, right, specifically when you take limits to negative infinity, so my point is generally when you're working with those functions other than the rational, taking limits to negative infinity, you do this right here for your safe work. You're gonna let x equals a negative z right here. Okay? You're gonna do that substitution. Okay? You're gonna do a substitution. So here's the thing. So think about it. If you let x equals negative z, right, then when x goes to negative infinity, it means the same as z is going to positive infinity. See what I'm saying now? So what I was saying just earlier, once again, this is a substitution that I highly recommend you to do anytime you're handling x to negative infinity. You don't need to do that when your function in the beginning was entirely rational, but when you're step outside of the rational function and working with the x to negative infinity, start doing this right here. As you let x equals to negative z, that means equivalently, as x gets close to negative infinity, right, it means the same as z gets close to positive infinity. Right? So I have a reason for that. So let's take a pause on that. So let's bring the problem, let's bring this method into our problem right here. So the problem starts, right, with x to negative infinity, and then your function is the square root, fancies, right, etc., x squared minus 7x plus 1, right, minus x. But remember, I'm going to substitute x equals to negative z. That means here's how the problem becomes. It becomes limits as z going to positive infinity, right? And then the square root expression gives me the x here is substituted by a minus z all squared minus 7 times minus z, right, plus 1. And then I'm subtracting a negative z. You guys with me on that still? So now look at this tremendous result that it's going to bring to us here. This tremendous consequence here. We turn out the limit problem into something completely in terms of z, right? But z or x, it doesn't matter. It's just a one problem. We're taking limits and we do it. But look at the square root expression. Minus z all squared inside the square root is going to give me just z squared, right? We can now ignore the negative sign. Right? Minus 7 times negative z. So minus 7 times negative z is going to make it plus 7z. It's just a small change, right? And then plus 1. So it's still a polynomial inside a root, right? And then subtracting the negative z gives me the plus z. Are we good with that then? Okay? So I'm taking a quick pause here a little bit for you guys to get caught up. And so now when we come to this, we turn the problem into just a square root term and then plus another term, right? Let's see what the basic limit law here. Basic limit law says you can do one limit for the square root term of the z squared plus 7z plus 1, right, as z goes to positive infinity. Right? And then plus, and then the limits as z for z as z gets to positive infinity. So it still seems fine, right? And then basic limit law says further that I can bring the limits inside my root. Yeah, so I can take the square root on the limits of z squared plus 7z plus 1. Right. Plus with limit z. Now let me rewrite that step there over here. There's the square root, limit of the z squared plus 7z plus 1 is here, right? Plus the limit of z to infinity, z is approaching infinity. Now I think I can get answer from you guys right here. What will this limit turn into inside the root? It's infinity, right? It's infinity because see, it's a polynomial in terms of z, right? We let z, so right hand behavior of this polynomial over here. Even degree, leading coefficient 1, I mean positive leading coefficient. So it's a square root of something that grows to infinity. Sounds good? What about this? Infinity, I mean this term right here. It also grows to infinity, right? But now, from what I said earlier, we are legally accepting that because this square root of infinity will also grow to infinity, right? So infinity added with something else infinity, yes, we will run to something that, in the end, all growing to infinity. So our final answer here is a positive infinity. So for this problem right here, right from the beginning, even though it was subtractions, and you may at first think about doing the multiplying the conjugate to that or whatsoever, right? But see, hold it. It goes to negative infinity, so before you even do the conjugate or whatsoever, change that to a negative z first, right? And then we didn't, as it turned out, after we do that substitution, we didn't need to do the conjugate. It turned into a square root plus a term. See what I'm saying? No? So it all of a sudden it changed our plan, right? So now it seems like it turns out a lot easier than we thought, right? And so that's how we handle with another problem with. The experience I want you guys to learn from this particular problem is that when you step outside of the rational, anytime you're working with x approaching negative infinity, do this. This is your first thing to do right there in line. Right? Do that substitution. You let x equal to negative z. You substitute every x by a negative z, but that also means the limit becomes z to positive infinity instead of x to negative infinity. Okay? So we've had a list of special limits, and I keep adding more special limits into your list right here. If you still have that page, or else you can still write it as an additional page. So some more special limits. And here we have solid proof, but eventually there'll be something that's special enough for you guys to consider. Let's look at this function right here, that's e to the x, right? So e to the x, but I want to let x approaching positive infinity. And then that once we're through with the e to the x, the same specialty about this e to the x is going to also apply to the other exponential as well, like a 2 to the x or a 5 to the x. But here's the idea. Generally speaking, for an exponential function, what does the graph look like? It's a one-way up, rising, right? Just like that. See, e to the x, 10 to the x, 2 to the x, all going to carry that fundamental shape right here. So think about it. For your e to the x, as you let x approaching positive infinity, if you keep navigating toward the right-hand side right here, what's happening to your right hand? It's going to keep growing up, right? So yes, this one here is legally positive infinity. You know it. Sounds good there? But then on the other hand, same graph, same function, exponential, right? Exponential function in general. But now what if you're looking at x to negative infinity? Think carefully. Same graph right here, but you're tracing to the left hand right here, right? What do you say that the answer is going to be? 0, right? 0. There you go. Okay, so limits to the right hand. I mean, the right hand behavior and left hand behavior is not always the same. When we step outside of of the rational function. So that's the exponential function. Aside from the exponential function, we also learn about the sine and the cosine, right? Think about this. What happened when we calculate this? The limit as x goes to positive infinity on the sine function. Sine function itself, you guys do remember what sine looks like? Yeah, it's that wave, right? So it goes up and down, up and down, up and down, up and down. And the same way right here. What do you think that limit is? As I keep going to the right-hand side, sometimes it head up, sometimes it head down, sometimes it head up. What do you say? What do you suggest that overall limit is going to have to be when you go to the right-hand point, or the right-hand behavior? Yeah? Okay, it's bouncing between -1 and 1. I understand with that observation, but as far as the final limit, where it's going, does it go to -1 always? Does it always go to +1? Only a few places, right? Does it go to 0 sometimes? Only a few, sometimes, right? So in the end, it has so many answers. Disagreements all over. So what do you say? Does not exist, right? You know what I'm saying? Because see, at some value it hits the peak, right? At some other value it hits the valleys, right? At some values it hits the 0. And then there are other values for x, it hits the halfway. See what I'm saying? No? It got all kinds of values here, so unpredictable, right? So we say it does not exist. And so same way over here, for sine of x, needless to argue, going to the right end or going to the left end of your graphic, that negative infinity or positive infinity is going to behave the same, coming out with a d and e. And this understanding will be also quite useful for your calculus 3 courses later on that come in your learning. Now, what about cosine? When you're looking at x going to positive infinity, for example, cosine goes like this, right? But in the end, it's still a wave that's up and down, up and down, up and down, right? So what do you suggest?
Would it be the same thing?
The same thing, meaning d and e, right? Okay. So going to the right hand, that means studying the right hand behavior of cosine. Yes, it goes to d and e. And what about the left hand? Behaves the same, right? Up and down, up and down, up and down. Okay. So these two fundamental trig functions, as you're learning about their and behavior, they go to d and e. The logarithm, when you're looking at limits to positive infinity, right, goes to positive infinity as well, because the graph goes like this. See that? Okay. But for this kind of problem, for this logarithm, we don't even learn about the left-hand behavior. You see the reason why? Yeah, because it's not going to even exist, right? I mean, the problem itself doesn't even exist. It's not about the limit. It's not even going to exist because logarithm does not have the negative side of that, right? It's only taking positive number. See what I'm saying? Huh? Okay, so a lot of times when you're looking at logarithm, people are only concerned about going to the right hand. Logarithm only go one side, right?